In this video, we're going to do some extra examples involving random variables. So let's get right in it. So example 1, suppose you reach into a hat that contains a quarter, a loonie, a toonie, and 3 poker chips, and you're selecting one of them at random. Okay, you get to keep any money that you select, but we want to know how much should you lose if you get a poker chip in order to make the game fair. Okay, so let's define our random variable x to be our, I'm going to say our winnings. Okay, now you want to be careful. I'm going to do this in dollars. Okay, you could do it in cents if you prefer. So what are our options? Okay, and then the probability of each. So we could win $2 if we get the toonie. We could win $1 if we get the loonie. We could win 25 cents if we get the quarter. Or we could lose some amount of money. I'm going to call that K. Okay, so let's just I'm going to write here. So pay K dollars if we select poker chip. Okay, so there are 1, 2, 3, and then 3 poker chips. So 6 coins in total. So there's only 1 toonie, so 1 out of 6. 1 loonie, so the probability is 1 out of 6. 1 quarter, so the probability is 1 out of 6. And for the poker chips, 3 of them out of 6 are poker chips. So that means we have probability of 1/2 of selecting a poker chip. So if we compute the expected value here, it's going to be 2 times 1 over 6 plus 1 times 1 over 6 plus 0.25 times 1 over 6 plus negative K times 1/2. Okay, so if we simplify this, this is 1 out of 3 plus 1 out of 6 plus 1 over 24 minus K over 2. So now we want the game to be fair. Okay, so fairness means that we want the expected value to be 0. So that means that I need 0 to equal all of these things. Okay, so this is 1/3 plus 1 over 6 plus 1 over 24 minus K over 2. So we want to solve for K. If I add up all these numbers, I think I get 13 over 24. Okay, so what that means is that K over 2 should be equal to 13 over 24. So that's if I add K over 2 to both sides, so that they disappear on that side. Now I want to multiply by 2 on both sides to get rid of the 2. So that means K is going to be 13 over 12, which if you make the decimal is $1.08. Okay, so this is, we need to pay $1.08 if we pick a poker chip in order for this game to be fair. Okay, let's try another one. So Sarah's looking to purchase some renter's insurance for her apartment. She's considering 2 options. So option A means, so she has to pay $8 per month, and they would pay $10,000 if the apartment's damaged. Option B is she pays $10 per month, but she gets $14,000 if the apartment's damaged. And suppose that she knows the probability or the chances that her apartment is damaged is 0.02%. Okay, so we want to be careful about that. So which one should she choose? So what I'm going to do is I'm going to have 2 random variables. I'm going to call it XA and XB, and we want to compare these. So XA is Sarah's net gain, let's say, under option A, and XB is Sarah's net gain under option B. Okay, so now we want to do each of these. So, or I should say for XA. So what are the options for X here? So if there's no damage, she's going to pay $8. So her net gain is going to be negative $8. Okay, but it's possible that her apartment will be damaged. And if it is, she gets $10,000 minus the $8 that she paid at the beginning of the month. So that's $9,992 would be our X value. Now we want to be careful. So maybe I'll do it over here. So they said the chances that it's damaged is 0.02%. Okay, this looks like a probability, okay, but it's not equal to 0.02. So 2% is actually 2 over 100, so that's 0.02. What we actually have is 0.02%, which should be 0.02 over 100, which is actually going to be 0.0002. Okay, so that's our probability. So the probability of damage is 0.0002. So the probability of no damage should be 1 minus that, so 0.9998. So we can compute the expected value here. So it's going to be negative 8 times 0.9998 plus 9,992 times 0.0002. And I think if you compute that, you get negative 6. Okay, now let's try for plan B. So it's going to look similar. So she might lose $10, and the probability that happens is still 0.9998. Or she might gain 14,000 minus the 10 she paid, so 13,990, and that has probability 0.002 of happening. So if we compute the expected value of XB, it's going to be negative 10 times 0.9998 plus 13,990 times 0.0002. And I think if we compute that, we get negative 7.2. Okay, so this in A, so on average, she expects to lose, because it's negative, $6 a month. Okay, but over here in XB, she should expect to lose $7.20 per month. Okay, so probably Sarah wants to pick A. So that she loses less money on average per month. So even though the payout is bigger in Plan B, because the chances of getting it are so small, it's actually better to pay less each month. Okay, let's try another one. So suppose a box has 5 red, 4 blue, and 6 green marbles. Okay, and our experiment consists of selecting a sample of 4 marbles at random. Okay, and X is going to be the number of green marbles in the sample. So P of 2 is going to be the probability that capital X equals 2, which is the probability that we select exactly 2 green marbles. Okay, so we're going to compute this by counting. So the sample space, okay, so let's see, how many marbles are there in total? So 9 and 6, so there's 15 marbles total. Okay, and we only care about green or not green. So we're picking 4, so the sample space is going to be 15, choose 4. And if we want exactly 2 green ones, from the 6 green ones, we're going to select 2. And then I need 2 more marbles, and they have to come from the non-green ones. So I'm going to do 9, choose 2. Okay, so this is not right. So I didn't compute these in advance. Okay, so this should be 0.3956 approximately. So maybe I'll write here. Select 2 green and select 2 that are not, non-green. Okay, now what's the probability we get at least 2 green marbles? So this is going to be, this is the probability that our random variable x is at least 2. So there's 2 different ways to do this. So we could do the probability x equals 2 plus the probability x equals 3 plus the probability x equals 4, because the most we can get is 4 since we're only selecting 4 marbles. Or you could do 1 minus the probability you don't get 2 greens, which is going to be the probability that we get 0 plus the probability we get 1. Okay, either way is fine. Both involve computing 2 cases because we've already done one of them. So I'm just going to do it directly. So we already know the x equals 2 case. Now I'm going to add the 3 case. So that's going to be 6 choose 3 times 9 choose 1 over 15 choose 4. And then I'm going to have all my 4 coming from the greens. Okay, so if we compute this, so this one here is 0.1319. And the last one is 0.011, essentially. Okay, so if we add these up, we're going to get 0.5385 as our probability here, approximate. Now, what happens if we perform this experiment 8 times? And we want the probability that we select at least 2 green marbles exactly 5 times. So this is actually kind of tough. And we're actually turning this experiment into a different experiment. So what I'm going to do is make a new random variable. So y is going to be the number of times that we select at least 2 green marbles. So y happens to be a binomial random variable. Okay, it's going to have my n, the number of trials, as 8, and the probability of success is the probability that we computed in part B, because it's the success here is that we get at least 2 green marbles. Okay, and then what we're looking for is the probability that y equals 5. So we want to know the probability that this happens exactly 5 times. So we can use the binomial formula. So it's going to be 8 choose 5, 0.5385 to the power 5, times the 1 minus this is going to be 4615, and we're going to need that to the power 3. And if we compute that, we get 0.2492 approximately. So we were counting how many times that this event that we did in part B happened when we did this entire experiment 8 times. Okay, so we turned a non-binomial thing into a binomial thing by repeating the experiment over and over again. Okay, when Brittany plays darts, there's an 80% chance that she hits the dartboard, or she gets the dart to stick on the board on a throw. Okay, and in a game of darts, she normally throws 25 darts at the board. So, what is the probability that Brittany hits the dartboard or sticks to the dartboard exactly 20 times during the game? Okay, so let's let x equal the number of darts that stick to the board, or that hit the board. Okay, then x is going to be binomial. So it's a binomial random variable. Now here, n, the number is the number of throws, so she does 25 per game. The probability of success, so there's 80% chance, so it's going to be 0.8. So that means there's a 20% chance that she misses the board or doesn't stick to it. So that's 0.2. And then what we're looking for is the probability that x equals 20. So it's going to be 25, choose 20, times 0.8 to the 20, times 0.2 to the 5. Okay, so if we compute this, we get the probability as 0.196, approximately. Now, how many times should Brittany expect to hit the dartboard? Well, now we're looking for the expected value of x. Now, be careful. So normally when we compute the expected value, we need the probability distribution table for the random variable, which is going to be big here because there's 26 different things that could happen. So she could hit the board from 0 to 25 times. But when we know our random variable is a binomial random variable, then we actually get a formula that we can use. So it's just n times p. So the n is 25 and the p is 0.8. So Brittany should expect to stick to the board. Actually, she should expect to do it 20 times. So we actually got a nice integer here. Doesn't have to be an integer though. Okay, one more example. Suppose the college is thinking about policing their own parking lots. Given the amount they intend to patrol the lots, they approximate the probability that students can park without paying and not get a ticket to be 0.15. What should they charge the students that they do catch if they wish to gain $20 on average? Okay, so let's let x be the college's parking gains. Okay, so we're ignoring the people that pay. Okay, so this is for tickets only. Okay, so the values for x. So it could be that they gain nothing. Okay, so this is for the students that get away. Okay, or they could ticket some of them. So they catch someone, they give them a ticket. Let's say the ticket they give is K dollars. Okay, so they estimate the probability people will be able to get away without paying is 0.15, which means there's an 85% chance they're going to catch the people. And what we want is we want to find K so that the expected value of x is equal to 20. Okay, so let's compute the expected value. So it's going to be 0 times 0.15 plus k times 0.85. So that's actually just 0.85k. So the expected value equals 20 means that 20 should equal 0.85k, which means that k should be 20 divided by 0.85. Which is $23.53. So the college should charge $23.53 for each ticket they give out in order to expect $20 on average.